In single variable calculus, the most useful thing you can do with the derivative is replace a curve, locally, by its tangent line. Zoom in close enough to a smooth curve and you cannot tell it from a straight line, and the slope of that line is f prime of a. Today we move up one dimension. A smooth surface z equals f of x, y has, at each point, a best linear approximation. But now the approximation is no longer a line. It is a whole tangent plane, tilted in two independent directions. The slope in the x direction is f sub x, the slope in the y direction is f sub y, and the plane's equation comes from those two numbers in one line. From the tangent plane, we read off the linearization capital L of x, y, which is the multivariable replacement for the tangent line's capital L of x equals f of a plus f prime of a times the quantity x minus a. We will use it to approximate a square root, to estimate a propagated measurement error, and to clarify what differentiable actually means in several variables. Quick recap from single variable calculus. If f is differentiable at x equals a, the tangent line at the point a, f of a has equation capital L of x equals f of a plus f prime of a times the quantity x minus a. That's the linearization. For x close to a, the value capital L of x is an excellent approximation to f of x. The error is not just small, but vanishes faster than x minus a, which is the meaning of little o of x minus a. We also write the same content as dy equals f prime of a times dx. A small displacement dx in the input produces a predicted change, dy in the output equal to slope times displacement. Geometrically, the whole content is the locally flat principle. Zoom in far enough to a smooth graph, and you cannot tell it apart from its tangent line. Today, we promote that idea to surfaces. In one dimension, we needed one slope. In two dimensions, we need two. A surface z equals f of x, y has, at each point, two independent ways to vary the input. Hold y equals b fixed and slice the surface with the vertical plane y equals b. You get a curve in three dimensions whose graph in the xz plane is z equals f of x, b, and the slope of that curve at x equals a is f sub x at a, b, the partial derivative we've been computing for several episodes. Hold x equals a fixed and slice the other way. You get a different curve, z equals f of a, y, with slope f sub y at a, b at y equals b. A rigid flat object passing through the point a, b, f of a, b and tilted to match both slopes is uniquely determined, and it's a plane. That plane is the tangent plane to the surface at the point. It plays the same role that the tangent line played in single variable calculus. Locally, the surface looks just like its tangent plane. Here it is, the tangent plane formula. At the point a, b, f of a, b on the surface z equals f of x, y, the tangent plane has equation z equals f of a, b, plus f sub x at a, b times the quantity x minus a, plus f sub y at a, b times the quantity y minus b. Three terms, the height of the surface at the contact point, plus a linear correction in the x direction with slope f sub x, plus a linear correction in the y direction with slope f sub y. Let's verify it does what we want. Plug in x equals a, y equals b. Both correction terms vanish, and z equals f of a, b. The plane passes through the contact point. Take the partial with respect to x of the right-hand side, the constant vanishes, the y term vanishes since there's no x in it, and the x term gives slope f sub x at a, b dotty matches. Take the partial with respect to y, by symmetry, slope f sub y at a, b dotty matches. The plane passes through the right point with the right two slopes, which makes it the tangent plane. A useful rewrite, move everything to one side, and the plane has normal vector with components f sub x, f sub y, and -1. The gradient padded with a -1 in the z slot. Hang on to that, we'll come back to it. Here is the picture to keep in your head. A smooth surface, I have drawn a bowl-like paraboloid, and a flat plane tilted so that it just barely grazes the surface at one point. That point is a, b, f of a, b, and the plane is the tangent plane. Notice what's happening at the contact. The plane and the surface agree in three things. They pass through the same point, they have the same slope in the x direction, and they have the same slope in the y direction. Those three agreements use up all three coefficients of the plane's equation. As you move away from the contact point, the surface and the plane peel apart, but slowly. The gap grows like the square of the displacement, not linearly. That quadratic gap is exactly what differentiability buys us, and is the same phenomenon as the tangent line in one dimension, where the gap between curve and tangent also vanishes faster than linearly. Zoom in far enough, and the surface and the plane become indistinguishable. Worked example 1. Find the tangent plane to the paraboloid z equals x squared plus y squared at the point above 1, 2. Three computations. First, the height of the surface there, f of 1, 2 equals 1 squared plus 2 squared, which is 5. So the contact point is 1, 2, 5. Second, the partials. F sub x equals 2x evaluated at 1, 2 gives 2. f sub y equals 2y evaluated at 1, 2 gives 4. Third, assemble the formula z equals 5 plus 2 times the quantity x minus 1 plus 4 times the quantity y minus 2. That's the tangent plane, and it's correct as stated. If you want it in slope-intercept form, expand 5 plus 2, x minus 2 plus 4, y minus 8, which is 2x plus 4y minus 5. So the tangent plane is z equals 2x plus 4y minus 5. Sanity check, plug in xy equals 1, 2, and you get 2 plus 8 minus 5, which is 5. Matches f of 1, 2. Take the partial with respect to x of the plane, 2. Take the partial with respect to y of the plane, 4. Both match the partials of f at the point. The tangent plane passes the three-way test. Same equation, second viewpoint. Define capital L of x, y to be the right-hand side of the tangent plane formula. F of a b plus f sub x times the quantity x minus a plus f sub y times the quantity y minus b, with the partials evaluated at a, b. We call capital L the linearization of f at a, b. Geometrically, capital L is just the function whose graph is the tangent plane. Pedantic footnote, capital L is strictly speaking affine, not linear, because of the constant f of a, b die, but everyone calls it the linearization anyway, and the name stuck. The point of the linearization is the approximation f of x, y is approximately capital L of x, y for x, y, near a, b. And the approximation is good in a sharp, quantifiable sense. The error between f and capital L vanishes faster than the distance. The square root of the quantity x minus a squared plus the quantity y minus b squared, from the base point, provided f is differentiable. In fact, that vanishing condition is the definition of differentiable in the multivariable sense. Having partial derivatives is not enough on its own. Pathological functions exist with partials everywhere, but no good linear approximation. And the technical job of differentiable is to guarantee that the tangent plane really does grab onto the surface tightly. Let me pin down the technical hypothesis precisely, because it is exactly what makes everything work. We say f is differentiable at a, b, when there exist two numbers, capital A and capital B. They will turn out to be the partials, such that the change in f from a, b to a nearby point, a plus h sub 1, b plus h sub 2 is well approximated by the linear expression capital A times h sub 1 plus capital B times h sub 2, with an error that, divided by the displacement length, the magnitude of the vector h, goes to 0 as the vector h goes to 0. That's the formal statement. The everyday language statement, the tangent plane fits the surface so well that the vertical gap shrinks faster than the horizontal distance you've moved. It is stronger than just having partial derivatives. Those only describe behavior along the axes, and pathological functions exist whose partials are well defined, but where the surface still has a kink or a crease that the tangent plane cannot grab. The good news, in practice, if both partials f sub x and f sub y exist and are continuous on a neighborhood of the point, then f is differentiable there. That's a sufficient condition that covers essentially every smooth function you'll ever compute with. So, for all practical purposes, has continuous partials, equals differentiable, equals has a good tangent plane. Worked example 2. Use a linearization to approximate the square root of 9.04 squared plus 0.05 squared in your head. Let f of x, y equal the square root of x squared plus y squared, which is the distance from the origin to the point xy. We'll linearize at the base point 9, 0, where the arithmetic is trivial. F of 9, 0 equals the square root of 81 plus 0, which is 9. Partials. F sub x is the derivative of the quantity x squared plus y squared to the 1/2 power with respect to x, which by the chain rule is x divided by the square root. It's the unit vector in the radial direction. At 9, 0, that's 9 over 9, which is 1. F sub y is y divided by the square root, which at 9, 0 is 0 over 9, which is 0. So the linearization at 9, 0 is capital L of x, y equals 9 plus 1 times the quantity x minus 9, plus 0 times the quantity y minus 0, which collapses to x. Evaluate at the point of interest, capital L of 9.04, 0.05 equals 9.04. Done. The true value is the square root of 9.04 squared plus 0.05 squared, which is approximately 9.04014. We were off by about 1.4 times 10 to the negative 4, or roughly 2 parts in 100,000, from one line of mental arithmetic. This is what linearization is for in practice, replacing a small nonlinear computation by a single slope step. The third face of the same idea is the differential, written dz. The total differential of z equals f of x, y at the point a, b is dz equals f sub x at a, b times dx, plus f sub y at a, b times dy, where dx and dy are small independent displacements of x and y. Compared to the single variable case, where dy equals f prime of a times dx, there was one product term, slope times displacement. In two variables, there are two product terms, one slope times displacement contribution for each coordinate summed. Computationally, dz is the same as the linear part of the tangent plane approximation. If you let dx equal x minus a and dy equal y minus b, then dz equals capital L of x, y minus f of ab, which is the predicted change in z when you walk from a, b to x, y along the tangent plane. The actual change in z along the surface is delta z equals f of x, y minus f of a, b. So delta z is exact, dz is linear, and the difference, which lives in the second-order Taylor term coming next episode, is what we ignore when we linearize. Worked example 3. The classic engineering use of differentials, error propagation. The volume of a right circular cylinder is capital V equals pi r squared h. Compute the partials. Capital V sub r holding h fixed is 2 pi r h. Capital V sub h holding r fixed is pi r squared. The differential is d capital V equals 2 pi r h times dr plus pi r squared times dh. Now apply. Suppose you measure r equals 5 centimeters and h equals 10 centimeters, each with uncertainty plus or minus 0.1 centimeters. The worst case error in the computed volume is the sum of the absolute values. 2 pi rh times the absolute value of dr plus pi r squared times the absolute value of dh, which at the measured values is 2 pi times 5 times 10 times 0.1 plus pi times 25 times 0.1. That's 10 pi plus 2.5 pi, which is 12.5 pi, approximately 39.27 cubic centimeters. The nominal volume is 250 pi, approximately 785 cubic centimeters. So the worst case relative error is 12.5 over 250, which is 5%. Notice the structure. The relative error is 2 times the relative error in r, plus 1 times the relative error in h. The exponents in capital V equals pi r squared h. That's a universal pattern for power law formulas. Engineers and experimental physicists use this every day to attach uncertainty bars to derived quantities. It is worth being precise about how the tangent plane and the gradient are related, because students often blur them together and miss that they live in different spaces. Both objects are computed from the same two numbers, f sub x at a, b, and f sub y at a, b. The gradient of f, the vector with components f sub x and f sub y, is a vector in the xy plane. It lives in the input space. Its job is to point in the direction of steepest descent on the level curve diagram, with magnitude equal to the maximum directional derivative. The tangent plane, on the other hand, is a plane in 3 space sitting on top of the surface z equals f of xy. Its job is to be the best linear stand-in for the surface near the contact point. They are two viewpoints on the same content. The bridge, if you walk in the xy plane in the direction of the gradient of f, the corresponding lift onto the tangent plane is the steepest uphill line in the plane, and the normal vector to the tangent plane is the gradient padded with a -1 in the z slot, the partials repackaged as an outward normal in 3 space. Same numbers, dual lives. Step back, why do we bother building this machinery? Because surfaces are locally flat is the structural fact from which a huge fraction of calculus and applied mathematics flows. First, plane approximation. F is hard, capital L is a single arithmetic expression, and near the base point they agree to high precision. Second, error propagation. The differential converts measurement uncertainty in inputs into uncertainty bands on derived quantities in one line. Third, critical points. When the gradient vanishes, the tangent plane is horizontal and the surface has a local extremum or saddle. We'll classify those next episode using the second partials test. Fourth, Newton's method in several variables. To solve a system of nonlinear equations, you iteratively replace each equation by its linearization and solve the linear system. Fifth, gradient descent. The workhorse of every neural network training run is literally step in the direction of steepest decrease, which is opposite the gradient, on the local tangent plane. Sixth, Taylor expansion, capital L is the first-order truncation of the multivariable Taylor series, and going further means adding a Hessian-weighted quadratic term, also next episode. The tangent plane isn't a cute geometric fact, it's the foundation. Recap. The tangent plane to the surface z equals f of xy at the point a, b, f of a, b has equation z equals f of a, b plus f of a, b plus f at a, b times the quantity x minus a plus f sub y at a, b times the quantity y minus b. 3 terms, height, x slope correction, y slope correction. Viewed as a function, the right-hand side is the linearization capital L of x, y, and f is approximately capital L near the base point, with error vanishing faster than the displacement length. That vanishing condition is precisely what differentiable means. In practice, having continuous partials is enough. Written in differential form, d as e equals f sub x times dx plus f sub y times dy. The multivariable version of dy equals f prime times dx with one slope times displacement term per coordinate. We computed the tangent plane to a paraboloid, used linearization to approximate a square root, and used the differential to bound the propagated error in the volume of a measured cylinder. We saw that the tangent plane and the gradient are two readings of the same two partials. The gradient lives in the input plane and points in the direction of steepest descent. The tangent plane lives over the graph and is the best linear stand-in. Next episode, we used these partials to find and classify critical points, where the tangent plane is horizontal, and what second derivative information tells us about the shape there. That's tangent planes and linear approximation. 3 viewpoints, 1 equation. As a plane, z equals f of a b plus f sub x times the quantity x minus a plus f sub y times the quantity y minus b, the unique flat object through the contact point with the right two slopes. As a function, capital L of xy, the best linear approximation to f near the base point, with error vanishing faster than the displacement. As a differential, dz equals f sub x times dx plus f sub y times dy, the predicted change in z under small displacements dx and dy. If this helped, like, subscribe, and post a comment with the answer to today's challenge. Find the tangent plane to z equals x times e to the y at the point 2, 0, and use it to approximate f of 2.1, 0.05. The exact value isn't far away. See how close your linearization gets. Next episode, we exploit the tangent plane at a critical point, where the gradient of f equals the 0 vector and the plane is horizontal, and we build the second partials test to decide whether we're sitting on a local maximum, a local minimum, or a saddle point. See you there. The tangent plane to the surface z equals f of xy at the point a, b, f of a b has equation z equals f of a b plus f of a bx minus a plus fy of a bi minus b, and the function L of xy defined by the right-hand side is the linearization of f at a, br. Locally, f of xy is approximately L of xy, with error that vanishes faster than the square root of x minus a squared plus y minus b squared when f is differentiable. Writing the displacements as differentials, the predicted change in z is dz equals fx of ab dx plus fy of ab di, the multivariable analog of di equals f prime of adx from single variable calculus. The tangent plane and the gradient are the same data viewed two ways. The partials fx and fy encode the plane's two slopes, and the gradient ∇f equals the vector fx, fy encodes the direction of steepest descent within that plane. We'll find the tangent plane to a paraboloid, linearize a square root expression to a fraction of a percent in one line of arithmetic, and use the differential to bound the error in a measured cylinder's volume. Next episode, we use these same partials to characterize critical points, where the tangent plane is horizontal, and the second partials test to classify them as local maxima, minima, or saddle points. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.